Hi, this is Math 8, Unit 5, Lesson 10 on piecewise linear functions. So we're going to explore functions built out of linear pieces. And linear pieces is where we kind of get the idea of a piecewise linear function. Just talking about lots of different chunks that come together to make one function. Okay? So, what do you notice? What do you wonder? So we take a look at this first little chart or graph we're talking about here. We have time, hours to midnight, and temperatures here, and things that we notice. We can see that our dots all seem to kind of go in an upward direction for a while, and then they tend to fall back down. But we notice that they're also not linear. We can see that there was an attempt to put in a linear model here, right, and to draw that line and line to approximate about what's going on with the temperature, but we can tell that's not fully accurate, is it? In the same sense, I can make a graph that says, well, I can go from here to here, and that line there, I can go to there, I can go here, I can go up, I can go a line there, kind of a line across, I can go down a little bit, go flat, I go down a little bit, go across, go down a little bit, right? So depending on how I want to see these dots, I can make different segments of this graph to chop it up in what I see happening from smaller chunk to smaller chunk, or just two big chunks. That's breaking things apart into linear pieces. And so today, we're going to start looking at this, okay? These are piecewise linear functions, which are multiple line segments, is what we're talking about here. Multiple line segments. We use our model and we chop our models into multiple line segments. And so we look here at modeling recycling in this picture here. And we have all these little points for when recycling, what percentage of the trash, whatever, was recycled in the various years. We've used this graph before. The first question we're being asked today is what percentage recycled, what approximate the percentage recycled each year with a piecewise linear function by drawing 3 and 5 line segments to approximate the graph. Okay, so we're going to try to draw some line segments here to approximate the graph. So depending upon what you did in class today, you might have some variance here, and that's okay. And so, I mean, I did mine first, and then I looked at my answer book, and I used some different times, different years. That's okay, not a big deal. So let's start here first of all at this point right there, which is at about, I have in 1991, we recycled approximately, we could say maybe 16% in 1991, and that'd be a fine place to start right there. I could then probably jump up here and say, well, this is pretty upward going until about this point in 1996, where maybe I'm at about 1996 and I seem to be at about 22%, something like so. All right, and that's maybe my first little line segment from 1991 to 1996. Now when I look at that line there, in terms of what the first question is, what's the percentage recycled each year? Okay, we can see that there's a growth there going from 16 up to 22. That's going to be an increase of about 4%. So we're going up about 4%, and we're doing that over the course of, in this case here, 1991, 1, 2, 3, 4, 5 years. So in the course of 5 years, we seem to be going up, in our case, 6%, up about 6%. 16 to 22 is 6% in the course of about 5 years. So it's an increase of 6% over 5 years. As a slope, we would say that it's our y over our x. We're going 6/5 as a slope there. So our slope would be 6/5 as a slope in that section right there. Does that make sense so far? So the next point could be something like, instead of 1996, we start from here, and what my book suggests is that I use 96, 97, 98, 99, right about there to be my next point. That one didn't make a lot of sense to me when I first started. I used this one here, and so I'm going to do that again because it makes more sense to go down from here to here in that small segment right there. So that small segment here is going to be at about 1996, 97, 98. So 1998, and then we probably dropped about 1%, maybe just a half a percent. Hard to really say because that's 21. So if that's 22 in between that, so let's go at 21.5% as our spot right there. So in that little line segment at 21.5%, we can see that we have, in terms of our percentage, we've decreased 0.5, right? We decreased 0.5% over the time period of 2 years. So that's what we have, 0.5 over 2. If I want to make that into, get rid of the decimal, what I could do is I can multiply everything by 2, okay? If I multiply this by 2 over 2, that's going to give me a 1 on the top and a 4 on the bottom. I do want to make sure I know that this is going down, so it's a negative, right? I'm decreasing, so my slope on this little part is a negative 1/4, decreasing there in terms of my slope for the percentage of recycling being done there. My next point that I plotted for my sake was over here at 2011, and that was at about, I said here, just again 26%, just approximating what that might be. So if I had made a line segment from here to here, it would look something like this, right? And so in this case here, what's taking place is with my Y value, I'm gone from 21.5 to 26. So 21.5 up to 26% is what's gone there. So that's going to be an increase of 4.5%, and that was done over the course of 1998 2011, over the course of 13 years. So that's what my slope would look like for that little segment there. And then finally I did the last segment, which was 2011 12 to 2013, like so, and that seems to be going to 2013 there. We are somewhere in the middle, so maybe 25, it really doesn't matter here, 25%. So maybe you have a decrease of 1 over the course of 2 years. So that's what your slopes would look like, and talking about the percent of change what's being recycled from those years. The whole point of this is recognize that what I have is I end up with different pieces, don't I? I have this piece of the graph that shows a slope of 6 to 5. I have this piece of a graph which shows the slope of 4.5 over 13. I have another piece of the graph here which shows that a negative 1/4. And I have another slope of graph over here which shows a negative 1 over 2. So I have 4 different chunks or segments of this graph showing me 4 different things happening over the course of time. And that's just fine. Graphs can do that as well. And it's a great way of modeling different stories or different events. Let's look at a story about a dog bath. And again, we just talked about this part here, so we just verbally did, so I didn't do that on the paper. It says Elena filled up the tub and gave her dog a bath. Then she let the water out of the tub. All right, this graph shows the amount of water that in the tub in gallons as a function of time in minutes. Okay, so it shows the amount of water as a function of time. So time is our independent and the water is dependent. How much water is in there depends upon how much time has passed. Whether I am filling up the tub, washing the dog, or draining the tub. So let's take a look at our questions. The graph shows the amount of water in the tub in gallons as a function of time in minutes. Add labels to the graph to show this. Check. Time's on the bottom, water's up on the side. When did she turn the water off? In this case, when did she turn off the water faucet? She turns it on here and it continuously increases until this point right there, and then it stops adding more water. When did that occur? Let's take a look at our time down below, and we recognize that took place at 6 minutes. So she turned the water faucet off at the 6-minute mark. How much water was in the tub when she bathed her dog? Well, let's assume that she puts the dog in when she turns the water off. All right, and this is when the bathing time starts, is right here. So how much water was in the tub? It looks to me like 24 gallons based upon the chart. Right, the graph. At 6 minutes, there were 24 gallons, and it's time to put the dog in the bath. Now she's going to bathe that dog, it looks like from here to here, right? So we could also answer how long the bath was. We have 6 minutes to 18 minutes, so it's going to be a 12-minute long bath for the dog. And how long did it take for the tub to drain completely? Well, we're going to wash the dog for 12 minutes, and then from 18 down to 30 is our draining time. So if we did 30 minus 18, we would see that it takes 12 minutes for the water to drain out. So 6 minutes to turn the faucet off at 6 minutes is 24 gallons at the time, and it takes 12 minutes for her to do the dog, to drain the tub. The next question, number 5, still about it, is at what rate did the faucet fill the tub? So the rate is going to be here for filling the tub. What was the rate of filling the tub? In our case, what we know is that we're definitely doing 24 gallons in 6 minutes. That's our current rate, 24 gallons in 6 minutes. I can reduce that though, because 6 goes into 24 4 times. So this is going to be 4 gallons every 1 minute, right? Or we can write this as 4 gallons per minute. That's my rate of filling the tub, is at 4 gallons per minute. This next question says, what rate did the water drain from the tub? So looking at our chart here, what is the rate of draining? We can see that again, we're going to be decreasing 24, so we're going down 24 gallons, and it takes how many minutes? From 18 to 30, we already know it takes 12 minutes. So we're decreasing 12 gallons over the course of 24 gallons over 12 minutes, which is going to be -2 gallons per minute. So that is my decrease value, or my draining value there. Okay, we're going to be going down 2 gallons per minute. Is what our rate is going to be in that case there. It's a question of, do you have to say it's a negative value there or a positive value? So you might want to talk to your partner real quick and kind of talk about there. Do you do a positive, do you do a negative? Well, in terms of the amount of water that's being lost, it is negative, but really the rate is still a rate, it's positive still, of 2 gallons per minute. We would still probably label this as a 2 gallon per minute as the rate, even though it is decreasing in terms of what's taking place there. The rate is still a rate. The rate is still going to be positive, but it's not a big deal right now. All right, let's move to the next activity. This one is an optional activity that you may or may not have done in class today, but I do want to do this because you'll have a problem very similar to it on your homework tonight. It says the graph shows the speed of a car as a function of time. Describe what a person watching the car would see. So you'll have something similar like this on your homework. So the car over time, right, is going, and we can see it's traveling pretty quickly. That's its speed, that's its rate, pretty steep rate there. And then the speed levels off and nothing changes over a long period of time. And then the speed starts to slow itself down. Okay, so what we know is that right here in the beginning part, we have some increasing speed going on in the beginning. And then we have a steady pace right there, constant speed, no change in the speed. And then we have a gradual slowdown to the point where we get down to 0. Okay, notice that the slowdown is a slower rate than the increasing speed. That's a little bit steeper. So we sped up faster than we slowed down. Okay. The "Are you ready for more" question is a good question. So I want to look at it real quick with you. It says this graph models the speed of a car or a function of time during a 3-hour trip. How far did the car go over the course of the trip? All right, let's take a look at this. It says that at first it goes the speed per miles per hour. He's going 20 miles per hour for this length of time here. Notice the time is in minutes. So for this section, I'm going to put it into little chunks here. For this section right here, we can kind of draw it like so. For this block of time, it's going 20 miles every hour, and it does this for how long? For 1 hour. So this chunk of time is actually going to be, the car has gone 20 miles in that block of time. When I look at the next block of time, from this point to this point, we can see we're traveling for 30 minutes, right? So 30 minutes is our length of time there. And for 30 minutes, we're going 30 miles per hour. 30 minutes is half of an hour. So if I can do 30 miles in 1 hour, how much can I do in half of that? Well, let's take the 30 here, and we're at 30, and we're going to divide it by 2, and that means we can do 15 miles in that 30-minute time period. When we look at the next section here, we also have a 30-minute time period again. All right, so it's my 30-minute time period. And in this 30-minute time period, we're going 50 miles in 30 minutes. So we're going to divide that by 2 to find out how much that would be in 30 minutes. So 50 divided by 2 is 25. In this next section here, we can see we're going 15 for 15 minutes. And we're doing 40 miles in 15 minutes. So this is going to be 1/4 of an hour. So this is 40 divided by 4, which is going to be 10 miles there. This segment here is also 1/4 of an hour. And we're doing 20 miles an hour. So we end up with a 20 divided by 4, which is 5. And then finally at the end here, for a 30-minute span, we're doing 10 miles an hour. Divide that by 2 because it's only half of an hour, and we have 5. So at this point, what we can do is we'll add up our 20, our 15, 25, 10, 5, and 5 for a combined total of 80 miles. So it's a great little chart here, again demonstrating a piecewise function, how you have different line segments there that show various bits of information. Okay, so these are examples of what we call piecewise linear functions. Piecewise linear functions there. And that is a graph, when a graph is pieced together out of line segments. And that's what a piecewise linear function is and what we're looking at today. So why don't you turn ahead and go work on your homework, and then we'll check it together. All right, here's the homework. Number 1. The graph shows the distance of a car from home as a function of time. Distance from home. So here he is probably at home because he's at 0, right? So that's home. At this point he's gone away and whatever. So describe what a person watching the car may be seeing. What you might see here is that a car drives to maybe the store. Okay, so it's driving a distance to a store, and then whenever it gets to that destination, it could be the park, it could be something else, driving away from home, it eventually stops and parks for a little bit. It's not moving, it's staying the same distance from home over a period of time. So there's a stop that happens here of some sort. And then maybe he goes to the store, he picks up some milk and cereal, and he decides to come back home, and he drives home a little slower than he went to the store and gets himself back home and arrives back at home. So that's just me verbally saying what took place there. I want you to write a little story about what takes place there. Okay, he drives to the store at a good rate, stops and goes shopping, gets back in the car, and drives home a little bit slower than what he did before. Number 2. It says the equation and the graph represent two functions. Use the equation y equals 4 and this graph to answer the questions. Well, where does y equal 4? exist. Y equals 4 is right here. Here is where y equals 4. There it is. Y equals 4. Having a great time. So y equals 4 is right there. So when x is 4, choice question A, when x is 4, the output of the equation is the output of the equation of the graph greater. Okay, so when x is 4, well, here's where x is 4. We have a point right here for the graph, and here's a point for the equation. Which one is greater? We would say that the equation is greater, right? At the equation, it's going to be at 4. At the graph, it's going to be at 3, so that's going to be greater. What value of x produces the same output in both the graph and the equation? This is a nice way of saying what is going to be the solution of the two equations. When does this one equal that one? Or we should say this, what point do they come together? And that's going to take place right here when x equals 6. So our solution is when x equals 6, it's going to be at the same point, right? And that's our solution to our equation right there. Let's turn the page and look at the next one. This one shows the graph. This graph shows a trip on a bike trip. I'm going to zoom out a little bit here because a lot of stuff for one graph. The trail has markers every 0.5 kilometers showing the distance from the beginning of the trail. Distance from the beginning of the trail. Alright, so here's our distance from the beginning in kilometers, how far you are from the trail, and we have the time. So we have a bike guy who's riding his bike on the trail, and he goes away from the beginning of the trail, takes off. Alright, doesn't seem to go any further away, but time is going on. Maybe he stopped there taking a break, goes further away and takes a little break, and then starts to come back towards the trail starting point there. And that's kind of our story. He starts at the beginning, goes away, pauses a bit, goes away, pauses a little bit, and then makes the ride back home. Starts off really fast and slows down a little bit getting there. When was the bike rider going the fastest? The fastest is going to be found by finding our steepest slope. Right? Where was the slope the steepest? And in our case here, it looks to me like the steepest slope is from here to here. Right? That to me is our steepest slope. And you could do the numbers on it to verify that, but it's going to be that. So we're going to say the steepest slope is between 2.4 and 2.6 hours. That's our steepest slope right here. That's our steepest little bit. When was the bike rider going the slowest? Now we're not going to count when he stopped because obviously that is pretty slow. But he's not going at all, so it's not going slow, he's just done. So when does it have more the flattest slope? And these are pretty steep. I noticed this point here, from here to here, is our smallest slope. So we would say that from 1.4 to this point right here, which is 2.2 hours, is when he seems to be going the slowest. During what times is the rider going away from the beginning of the trail? So when was he going away from it, moving a distance from the origin? That happens really in a couple spots. We could say that we could definitely say that from 0 to this point here, which is at 2.4, the whole thing, he's definitely going away for the whole thing. He doesn't start to come back until there. But it might be better to say he's going away from 0 to 0.8, right? We could do it in segments from 0 to 0.8, and going away from this point here, 1.4, to this point here, which is 2.2. That would be acceptable. Or you could say he's going away from 0.0 all the way to 2.2. That could work there. Just be able to explain why you think what it is you want to say, right? He's not getting further away at 2.4, but he still is away and hasn't made his way back. So you can describe that in your own way. During what times is the rider going back towards the beginning of the trail? We would say that's going to take place from definitely 2.4 to 3. This segment here is going back towards the beginning of the trail, the return journey. During what times does the rider stop? And that is clearly here where the line goes parallel to the x-axis. So that's going to be from 0.8 to 1.4 is one stop. And our second stop is here at 2.2 to 2.4. Those are our stopped points. And our last question today says the expression negative 25t plus 1250 represents the volume of liquid of a container after t seconds. The expression 50t plus 250 represents the volume of liquid in another container after 2 seconds. What does this equation mean in this situation? All right. So this is like I have container number 1 and container number 2. And when I'm setting them equal to each other, what does it mean? And that would be the place where the volumes, because we're doing the volumes, where the volumes of the two liquids are going to be equal, right? We're looking for where they're equal or where they're the same. We've set the two equations equally to each other, so we're going to find the place at which they have the same amount of liquid inside of them, okay? That's where they equal. And we call that the solution of our equation, where these two things are going to finally meet and match. All right? You don't have to solve it. You just have to be able to explain that. And again, your job is to explain equal, same in your own words. That's it for today. We'll see you next time.